Movement on a construction site involves massive transfers of kinetic energy. When a pedestrian occupies the same physical space as heavy mobile plant, the human body absorbs that energy, making site transport a primary vector for severe injury and death. This chart maps out fatality and injury data compiled by the Health and Safety Executive, or HSE. It reveals a stark contrast. While slips and trips account for a massive volume of total site injuries, their associated mortality rate is relatively low. Conversely, incidents categorized as struck by a moving vehicle or struck by an object yield a disproportionately high number of fatal injuries. This data dismantles a persistent industry myth, the idea that transport safety is achieved by simply telling drivers to be careful or reminding pedestrians to look out. Human attention degrades under fatigue, distraction, and schedule pressure. True safety is engineered. It requires physically decoupling pedestrian pathways from mobile plant workflows so that a lapse in human concentration does not result in a physical collision. Managing transport risk requires a systemic approach where the environment is designed to prevent fatal energy transfer, regardless of individual human performance. To manage this effectively, and to satisfy the rigorous requirements of the NEBOSH assessment, we must organize all transport risk controls into a specific framework, the tripartite system. This system is built on 3 interlocking pillars: the safe site, governing spatial geometry; the safe vehicle, governing mechanical suitability; and the safe driver, governing procedural protocols and competence. Physical segregation within the safe site pillar is the ultimate objective. Anytime you are forced to rely on the procedural controls of the driver to prevent an accident, you are operating in a degraded, high-risk state. This tripartite model scales universally. The same principles govern a closed, high-traffic logistics yard and the movement of company vehicles out on the public highway. NEBOSH examiners demand this systemic approach. They are not looking for a random list of safety tips. They expect you to apply the hierarchy of controls through these 3 distinct pillars. The foundational pillar is the safe site. Here, the focus is entirely on spatial geometry, traffic routes, and physical boundaries. This animated site plan maps pedestrian desire lines. These are the natural, shortest paths people instinctively want to walk to get across a site. When these intersect with heavy plant routes, they create high-probability collision nodes. You must engineer vehicle routes to deliberately avoid these desire lines. This is achieved by implementing mandatory one-way systems to eliminate reversing, and by designing the layout to minimize blind corners where visibility drops to 0. The physical terrain matters just as much as the routing. Haul roads must be constructed with appropriate materials, adequate drainage, and gradients that do not exceed a 1:10 ratio. Steeper inclines severely degrade vehicle braking performance and increase the risk of traction loss. Total physical segregation is the standard. This means installing robust pedestrian barriers, utilizing bump banks on the edges of steep inclines, and engineering clearly defined, well-lit crossing points. This geometric planning must also extend the site's external boundary, specifically when construction activities disrupt public highways and pose hazards to the general public. This schematic details the strict statutory requirements mandated by the New Roads and Streetworks Act. Protecting the public requires a heavily controlled sequence: advanced warning signs, a taper zone to merge traffic, an empty safety zone to absorb impacts, and finally, the enclosed working space. The barrier requirements for these streetworks are rigid. To ensure detection by approaching traffic at night, the regulations mandate the use of fully retroreflective red and white planks for all vehicular traffic barriers. Rigorously engineering the layout of the internal site and the external boundary removes the hazard of collision spatially. When paths never cross, subsequent vehicle or driver failures are far less likely to result in a fatality. The second pillar, the safe vehicle, requires strict mechanical suitability and a rigorous, documented maintenance regime. An examiner expects you to match a vehicle's physical specifications precisely to the site's environmental constraints. A diesel excavator operating safely outdoors becomes a deadly asphyxiation hazard indoors, requiring a switch to an electric model suited for confined spaces. This cross-section highlights the critical engineering controls required to protect an operator during a catastrophic event. Specifically, ROPS, rollover protection systems, which maintain a survival space if the plant tips, and FOPS, falling object protection systems, which deflect heavy debris away from the cab. Beyond structural protection, you must account for the hidden hazard of 360-degree driver blind spots. Mitigating these requires mechanical visibility aids, including reversing alarms, specialized mirrors, and closed-circuit television cameras. Mechanical aids are only effective if they function. This introduces the strict requirement for daily preventive maintenance, relying directly on the driver to conduct mandatory checks at the start of every shift. Drivers must verify roadworthiness using the powder checklist: petrol and fuel levels, oil, water and coolant, obvious visual damage, electrical systems including lights and indicators, and rubber, meaning tire pressure, tread depth, and sidewall integrity. Formal servicing falls to vehicle maintenance engineers, who face severe, specialized hazards. These include the risk of explosion from overinflating split-rim wheels, the ignition of battery gases, and the lethal crushing hazard of working beneath unsecured raised tipper bodies. A safe vehicle is a technologically augmented piece of plant, maintained rigorously to ensure it fails safely even when subjected to extreme forces. The final and inherently most vulnerable pillar is the safe driver. This covers the procedural controls, training, and direct actions of the human operator. The most prominent procedural control is the banksman, or signaler. Examiners view the use of a banksman as a high-risk activity. It is a concession that should only be implemented when physical segregation and site layout design have completely failed to eliminate reversing hazards. When absolutely necessary, banksman operations require strict mechanics. The signaler must wear high-visibility clothing, position themselves at a safe distance from the tipping zone, and use officially standardized hand signals understood by all operators. There is one absolute safety rule for reversing plant. If the driver loses sight of the banksman in their mirrors for even a single second, they must stop the vehicle immediately. Baseline competence for drivers extends beyond holding a standard license. It requires specific, formal training on the exact type of vehicle being used, explicit site authorizations, and ongoing assessments of their physical fitness to drive. Because procedural controls rely entirely on human compliance, they are the weakest link in the hierarchy of controls. Preventing fatal errors here demands intense, continuous management supervision. An employer's legal responsibility does not end at the site gate. Transport risk expands outward to cover work-related driving on public highways. The legal reality is absolute. An employer's duty of care applies equally to a sales representative driving their personal car to a client meeting as it does to an excavator operator moving earth on site. Controlling this off-site risk requires strict administrative checks. Employers must verify that the vehicle holds a valid MOT certificate, the mandatory UK test of roadworthiness, and that the employee possesses appropriate business insurance. These documents must be inspected and verified annually. Management must also control the human factors of journey planning. This means setting realistic work schedules and delivery targets so that drivers are not pressured into dangerous speeding to meet impossible deadlines. Fatigue management is equally critical. Employers must monitor working hours and ensure drivers take adequate rest breaks to combat the slower reaction times and poor concentration caused by exhaustion. Work-related road risk functions as a heavily regulated, legally binding extension of the company's health and safety management system. Securing high marks on the NEBOSH exam requires you to synthesize these concepts. The safe site, the safe vehicle, and the safe driver must operate together as a single integrated architectural system. Remember the core examiner priority. Spatial segregation and physical barriers will always supersede procedural rules and driver caution. A failure in one pillar cascades through the others. A poorly designed blind corner, a site failure, cannot be neutralized by driver training alone. The environment itself must be corrected. This integrated system is constantly tested by fluctuating environmental conditions. Deteriorating weather, poor lighting, and eroding surface gradients demand that control measures be dynamically assessed and maintained. The ultimate goal of transport safety management is designing an environment where inevitable human error is absorbed by the system, ensuring a mistake does not equal a fatality. For your rapid recall checklist, segregate routes to eliminate desire line intersections. Maintain plant through daily powder checks. Train and authorize drivers. and manage off-site journeys through schedule and fatigue control. Construction transport safety is an ongoing engineering challenge. It requires constant review, rigorous maintenance, and strict supervision to ensure the boundary between moving metal and the human body remains intact.